This video is going to be about understanding ring-type molecules, cyclic molecules. And what I wanted to start with is conformations of cyclic molecules. And in particular, I'm going to highlight something that shows up in your book, and that is that cycloalkanes have a lot of strain. And the reason why the molecules have strain is something that can be understood partially based on conformational analysis of straight-chain molecules. However, even after we do that analysis, you will probably notice that there ends up being additional strain unaccounted for. And we'll talk about that a little bit. For now, though, this is a chart that shows up in your book, and what I really want to point out is that very small molecules are highly strained. Propane, cyclopropane, and cyclobutane rings are really strained, whereas cyclopentane rings and cyclohexane rings really are not. Nevertheless, because of the relative ease of formation of small rings, 3 and 4 membered rings happen a fair bit. 5 and 6 membered rings happen absolutely everywhere, largely because they aren't particularly strained. It becomes relatively harder to find examples of the medium rings because though the strain isn't all that bad in those, it's harder to make them in the first place. So why is there so much strain in a small molecule like cyclopropane? Well, one problem is with that little conformational flexibility, the molecule almost always ends up fairly eclipsed. And so if you look at cyclopropane, what you have is an enormous amount of torsional strain where the hydrogens are all eclipsing each other. Just looking at this particular image, you can see that there's 2 kcals per mole higher than if they were staggered, one for each of these eclipsing hydrogen interactions. But we're not even considering these 2 hydrogens eclipsing these 2 and those 2. So there's at least 6 kcals per mole of torsional strain just due to eclipsing hydrogen interactions. And that's not the main problem with cyclopropane. The main problem really is that the bond angles here are very acute, and we would love for these bond angles to be 109.5, which means that the orbitals aren't really pointing at each other very well. In fact, you get a feel for this if you try to build cyclopropane with your model kit. You'll notice that you have to bend the bonds in order to make it work, and that's a sign really that there's a lot of strain. This molecule isn't happy in this form. There's an enormous amount of strain. On the other hand, it's relatively straightforward to get the ends to wrap around and meet each other. So there's low entropy costs associated with making a molecule like this, even as there's a high enthalpy cost for making it. The upshot is the cyclopropanes exist a fair bit, but they're really strained and would like to pop open if they can. The cyclobutane analysis is similar, but not identical. I mean, the 90-degree bond angle is bad, but it's nowhere near as bad as 60, so there's less penalty for the actual bonds. On the other hand, you do get a little bit more flexibility, a little bit of an ability to get out of a purely eclipsed conformation into a staggered conformation, although there's only so much wiggle room available. The upshot is that the total amount of strain in a cyclobutane ring is really similar to that in a cyclopropane ring. Cyclopentane is kind of unusual in that the bond angles at each one of these intersections is actually just about perfect. It's 108 instead of 109.5, and you would think that would be good. Unfortunately, though, the molecule has to exist largely planar, which means that there is going to be a significant amount of eclipsing interactions. And though you can make the molecule pucker to some extent, you really can't get away entirely from the eclipsing hydrogen interactions. So that's the source of the strain in a cyclopentane ring. The bond angles are great, but there's always going to be some eclipsing interactions that you can't get away from. And so the reason why we care about cyclohexane molecules more than anything else is that in the chair conformation that we've already described previously, if you look down any of these Newman projections, what you see is everything is staggered. There is no torsional strain of any kind, and the bond angles get to exist at 109.5. If you look at each individual set of 2 carbon atoms, each carbon atom is perfectly content. The bond angles in 2 dimensions are 120 degrees, but we know that that's not the way the molecule actually sits. It sits instead in a chair, and in the chair conformations, there is no angle strain and no torsional strain. This is the best possible situation. This is really a reminder that you've already seen the equatorial and axial hydrogens idea before. In the chairs and boats video that I generated for the stereochemistry segment, we walk through chairs, chair flips, the fact that equatorial hydrogens exist and that axial hydrogens exist. I really want to point out this image, though, that where these blue hydrogens are in the 3-dimensional space-filling model really is the equator of the ring. It doesn't seem that obvious when you're looking at a ball and stick model, but when you're looking at the space-filling model, those really are right around the belt line of this ring, and the axial hydrogens are really above and below. Again, I've walked through how I personally draw these chairs, and my advice to you is not to start with the 2 segments that they draw, but instead to start with these green segments first. But that's really a matter of personal preference. The whole point is, if you're drawing a chair conformation, make sure you use parallel lines for everything that you draw, and the axial hydrogens will be straight up and down, and the equatorial hydrogens will be parallel to other bonds in the chair. You may not have focused enough attention on this segment in the book, but this really is the right way to draw chairs.
I was just describing the Newman projection surrounding a six-membered ring. So here we are looking at a cyclohexane from the top, and the Newman projection will look like this. And this is kind of hard to see what's going on because all of the carbons are gray and the hydrogens are white. So what I'll do is shift to ChemDraw shortly, but what I do want to point out is that at this position here on top, there's a hydrogen that's coming directly toward you, which is difficult to draw in ChemDraw. And likewise, at this position here down at the bottom, there's a hydrogen that's going directly away and is obscured by the carbon in front. But this is what the Newman projection looks like in ball and stick form. So now let's examine it in ChemDraw. So in ChemDraw, here's the six-membered ring with the axial hydrogens in red and equatorial hydrogens in blue. And when I try to convert that into a Newman projection, what you can see is that these two carbons in front become these Newman centers here. And at this position, the carbon atom has a hydrogen pointed directly toward us that I haven't drawn. And at this position, the carbon has a hydrogen pointed directly away from us in blue that I haven't drawn. But you can easily translate a six-membered ring into two side-by-side Newman projections that happen to be connected together in this way. So this is why I'm talking about the Newman projections and why there's so little strain involved. We are in staggered conformations all throughout, and if you were to rotate the molecule sideways, you'd be able to find other Newman projections along the way. For example, this one, or say this one. Any different set of Newman projections you look at in cyclohexane all end up being staggered as long as you're in the chair. That's why there's very little strain involved.
Some strain starts appearing in the boat conformation, but that's why the boat conformation is not a major contributor.
And down here in the bottom right corner, you can see what is starting to be a pair of Newman projections, although this is with the model. And you can see the eclipsing interactions between these two hydrogens, the two carbons, the two hydrogens, two carbons, and the two hydrogens. And with each one of those interactions being about 1 kcal per mole, you can see why the boat conformation has a strain energy that's basically 6 kcals per mole. It's largely due to the eclipsing interactions. The twist boat is better because if you are very slightly out of this conformation, then some of those eclipsing interactions go away.
One thing I don't like about this particular image is that it implies that when you go from a chair to another chair that you have to pass through the boat. It's not true. You can, in fact, choose to pass through the boat, and if you are holding a model in your hands, my advice is that you do pass through the boat conformation, largely because it's easiest. If you hold the 4 atoms constant that aren't moving, you really flip down one headrest and up the other headrest, and you end up in the other chair. But in the meantime, you pass through the boat. Still, you don't have to go that way, and this energy diagram really shows you why. There's an enormous amount of torsional strain that you pass through on your way through a half chair, and so if you have to go through the half chair on your way to the boat, then you're going over this very large hump. So don't get the impression when you're interconverting between chairs that there's a specific path that the molecule will take. The message from this slide is really that though there's a large amount of energy associated with going over this hump, this is a relatively small amount of energy relative to what's available at room temperature. These molecules will interconvert about 100,000 times a second. They are constantly moving. They're sampling all the conformations. It's just that their dwell time will be longer in whichever chair is the most stable. And then I need to dwell a little bit on this table here, which is what is the energetic cost associated with putting a specific group in the axial position as opposed into the equatorial position. And really the one that you need to remember is a methyl group. And as you'll see when I hold up the model, the reason why this number is about 1.7 kcal per mole is that really this is 2 gauche interactions that suddenly arise, and that's your 0.9 twice, so that's 1.7 kcal per mole. As these groups get larger, this becomes a more significant contributor, larger and larger energy. T-butyl is also of interest, and it's 4.9 kcals per mole, and the reason why this matters is because even though that doesn't seem like a lot of energy, it's enough to guarantee that for all intents and purposes, this group is never axial. The 4.9 kcals per mole isn't that much, but it also means that this group will never be axial in the chair. This group will always be equatorial. How does that energy calculation work? So if we're examining the case where we have methyl cyclohexane specifically, the difference in energy between the methyl equatorial and the methyl axial is about 1.7 kcals per mole. But if you plug that into this equation, delta G equals minus RT ln of K, what that gives you is a K value of 18, which doesn't necessarily sound like much, but what it does mean is that you have about 95% of the molecule existing with the methyl in the equatorial position and only about 5% with the methyl in the axial position. It's 95.5 when you have 1.7 kcals per mole. So when you have 4.9 kcals per mole, this essentially ends up being 10,000 to 1.
Okay, so here we are once again going to manipulate a cyclohexane that is currently sitting in a chair form. One thing I want to point out is that when we are shifting from a chair to a boat or to other conformations, we almost certainly have to pass through this half chair situation, which looking down on it from the top, you can see that what we have is one thing puckered up and the rest is essentially flat. And for strain purposes, what this means is that all of these hydrogens are eclipsed. And so we actually have 10 hydrogens that are all simultaneously eclipsed, which is why this strain energy is 10 kcals per mole. So you go through the half chair. You don't necessarily need to pass through the boat because you can pass through some form of twist chair, but where you eventually end up will be either the chair again, where this methyl group, it's red, but it's methyl, is axial, or the alternative chair, where that group is now equatorial. I have chosen the color of the balls to represent, again, axial versus equatorial hydrogens. So all of these blue hydrogens are equatorial hydrogens, and these red hydrogens are the axial ones. And so you'll note, again, that if we are in the form where the methyl is axial, it is red along with all these other hydrogens, and then all of these blue ones are equatorial. But if we do the chair flip, then the methyl ends up equatorial along with the other red hydrogens, and the blue hydrogens now end up axial. So why is it that we have 1.7 kcal per mole higher in this conformation? And the answer to that is easiest to see in this Newman projection right here. The relationship between this methyl and this CH2 group is that they are gauche, and that is 0.9 kcals per mole higher relative to this particular carbon. However, if we rotate around and sight down the other bond, so once again that this is in the back, then we have another gauche interaction with this particular group right here. So this carbon, this set of hydrogens is gauche, and this is another 0.9 kcal per mole. So if we're looking at this methyl, there are really two different hydrogens that both offer 0.9 kcal per mole higher. It's these two right here. These two hydrogens are providing what we call a 1,3 diaxial interaction. 1, 2, 3. 1,3 diaxial interaction. So one thing that might have struck you as kind of strange in the table of A energies, which is to say what the cost of an axial substituent is versus an equatorial substituent, is that ethyl and methyl are really almost identical in terms of energies. And the reason why that might strike you as strange is because this methyl can reach around now and touch these hydrogens. You can make it touch. And so if this can be over here, why is it not more of a problem to have an ethyl group instead of a methyl group? And the answer is largely because so much of the time this can be flexed out here where there's no interaction that's worse for the ethyl group than the methyl. Again, the source of the strain for a methyl group is really the A13 interaction, the fact that this is gauche relative to these axial positions. And so that's still true, and even though the ethyl can interact over here, largely the ethyl will spend most of its time rotated away. By the same token, if we now have an isopropyl group at this position, you might imagine that this would be problematic because there's greater number of conformations where this is hanging out on top of the two axial hydrogens, and that's true. On the other hand, there's still a significant number of conformations where the methyls are pointed out away in space. And so isopropyl is significantly worse than ethyl. Say 2.2 kcals per mole as opposed to the 1.8 for the ethyl and the 1.7 for the methyl. But really, it's in the same general category as methyl and ethyl. It's about 2 kcals per mole rounded. Where things really change is when we attach one more methyl and now have a tert-butyl group, nominally possibly in the axial position. And here the problem is that no matter how you rotate the molecule, one of these methyls is almost certainly interacting with one of these axial hydrogens. And it really can't be avoided. No matter how we rotate it, there's going to potentially be contact between the methyl and these hydrogens. This is to say you actually have direct contact between the hydrogen on the methyl and the hydrogen here. Because that can't be avoided, all of a sudden we shift from about 2 kcals per mole to about 5 kcals per mole. And the difference then is sufficient such that the t-butyl group will almost always be equatorial. Again, the value is about 5 kcals per mole, and if you work through the energy, the delta G, then about 10,000 to 1 preference for this group to be equatorial as opposed to axial. And that's because out here it can rotate freely, whereas all of a sudden you put it into the other chair form and now it will be interacting with those hydrogens that are at the 3 position relative to the tert-butyl. If you now imagine that this is an OH, so oxygen with a hydrogen bound as opposed to a methyl, then you can see why oxygen is less of a problem than a methyl, because these two are lone pairs. They're not actually sticking out into this space in quite the same way. And so really, you have the ethyl thing again, where the hydrogen can mostly point out into this area and not interact with the hydrogens at the 3 position. So, more or less, what you need to remember is that the problems in the axial position are almost always due to negative 1,3 interactions, diaxial interactions. Or alternatively, another way of thinking about it is that anything that's axial will create gauche interactions, if you're looking at the Newman projections. Your preference for one chair over the other will be set almost entirely by these energies, and 2 kcals per mole is sufficient to have a 95:5 or better preference for one chair over the other. And always, you would prefer this group to be equatorial. The hydroxyl, the OH group axial, is better than methyl, but there's still going to be a preference to put it at the equatorial position as opposed to the axial position. All substituents want to be equatorial. If you have multiple substituents, then you have to choose between relatively larger groups and relatively smaller groups. Naturally, you'll try to put the biggest groups equatorial first. So, in a direct competition between tert-butyl possibly being axial and hydroxyl being equatorial, you will almost always favor the tert-butyl being equatorial. The tert-butyl is so big that its preference will dominate. It will always be equatorial, and all other substituents would prefer to be axial instead.